Okay, today we're going to do a lesson on similar solids. A lot of this stuff we've talked about, and we're going to use it a few more times and really try and drive it home, which it needs driving home. So when we're talking about similar solids, we're going to talk a lot about scale factor. And we should know that scale factor is the relationship, just simply put anyway, the relationship between dimensions of similar solids or even similar shapes. And that relationship would extend to perimeters too, because perimeters are just dimensions added together. But if we take the scale factor and square it, that number would help us determine the relationship between areas of similar solids or similar shapes, or lateral surface areas or surface area. So we'll say the relationship between areas including surface area. And then if we take the scale factor and we cube it, the number that we get would help us describe the relationship between volumes of similar solids. So all of these relationships we've talked about this year on several occasions, and we're going to use them to answer these next three questions, starting with this one. The two cylinders are similar. If the lateral surface area of the smaller cylinder is 20 pi inches squared, then what is the lateral surface area of the larger cylinder? Well, the first thing we want to do is determine the scale factor. So we got a height of 2 on the smaller one and a height of 3 on the bigger one. We know they're similar. They tell us that. That's a scale factor of 1.5 because 2 times 1.5 is 3. Okay. Now, so the ratio of their scale factors or their dimension is 1 to 1.5. But the ratio of their surface areas, or 1.5 to 1 if you're going from larger to smaller, the ratio of their surface areas is 1.5 squared to 1, or 2.25 to 1. So if we want to figure out the lateral surface area of the bigger one, and we're given the lateral surface area of the smaller one is 20 pi inches squared, we'll just multiply that by 2.25. Which is 45 pi inches squared. So we got to use the scale factor to figure out that the areas are 2.25 times as much on the bigger one, and then we'll take that smaller lateral surface area and we'll multiply it by 2.25 to get the bigger lateral surface area. Now, what about volume here? The volume of a model car built to a 1 to 20 scale is what fraction of the volume of the car? So every 1 unit of length on the model is equal to 20 units of length on the car. So 1 inch on the model is 20 inches on the actual car. But they're talking about volume. So when we're talking about volume, we want to take the scale factor and we want to cube it. So we'll do 1/20th cubed, which is 1/8000th, and that's our answer. Meaning, 1 cubic unit on the model represents 8,000 cubic units on the model, or on the actual car. So 1 cubic inch on the model is 8,000 cubic inches on the actual car. Pretty easy problem if we just know the relationship. Okay, a toy doll modeled after an infant is a 1 to 3 scale model. The amount of material required to clothe the doll is about what fraction of the amount of material needed to clothe an infant? Well, I think we're talking about surface area here, so how much clothing we'll need. We're talking about surface area to cover the doll. So that's scale factor squared. So we'll just take the scale factor 1/3 and we'll square it, and it's 1/9, meaning every square inch of clothing that it takes to cover the doll is going to be equal to 9 square inches of clothing that it would need to cover an actual infant, as opposed to 1 inch of height of the doll represents 3 inches of height of a real infant. Okay, so if we just get these down pat, and we've talked about them several times, it should make these problems very easy. We just need to identify which relationship to use and what information we're given and apply it properly. All right, we'll work on it in problem sets as we've been doing all year, and I'll be here to help you. See you tomorrow.